Greetings! Welcome to Electronic Circuits 1. I am Behzad Razavi and this is lecture number 44. Today we will consider a few more applications of circuits that use op amps and see how op amps play an interesting and critical role in these circuits that implement certain functions. But before we go there, let's take a look at what we covered last time in our study of other circuits that included op amps. We saw that we could build a unity gain buffer by simply connecting the output of the op amp to its inverting input. And we saw that the voltage gain from the input to the output is about 1. That doesn't seem very exciting, but if you remember that the input impedance of the op amp is very high, and the output impedance, especially after we make this connection, is very low. It was something like R out divided by A0 plus 1. Then we see that this is a good buffer for voltage quantities. It can sense a voltage with minimal disturbance, and it can deliver a voltage without being affected by heavy loads connected out here. We considered two other circuits that incorporate capacitors. We saw that if we go to an inverting amplifier and replace the feedback resistor by a capacitor, then the circuit becomes an integrator. And we can see that the transfer function is 1 over R1 C1s, or the output is the integral of the input with respect to time. So that's a very useful function to have. Another function is differentiation, where we replace the input resistor with a capacitor, and the feedback is still a resistor. And that gives us a transfer function given by minus R1 C1s. So that's the differentiator, meaning that the output is the derivative of the input with respect to time. We saw that because this circuit tends to amplify high frequency noise, we don't use it very often. Most often we use integrators. In other words, even if we have a differentiation somewhere, we try to maybe integrate both sides or something so that we do end up with integrators, not differentiators. All right, so what we saw before, the inverting and non-inverting amplifiers, the unity gain buffer, the integrator and differentiators are considered the linear operations. As you know, these are all linear systems. But op amps can also give us interesting nonlinear operations in conjunction with other types of devices. And today we will study a few of those here. So today we'll spend some time on nonlinear functions that incorporate op amps, again to create interesting implementations. And then we go to some imperfections of op amps and see how they affect the performance of these various circuits that we are studying. All right, so let's begin with nonlinear functions. And the first example I wanted to show you is what we call a precision rectifier. We have to see why we call it precision rectifier and then how we build it. All right, well, let's rewind to the beginning of this course when we learned that a simple diode could give us rectification. So if you remember, with the diode, this is what we did. So we built a simple rectifier. And we took a diode like this. We connected a resistor from the output to ground. And this was the input. And this is the output. And we saw that, for example, if you plot the input-output characteristic of this circuit, this is what we see with a realistic diode, or somewhat realistic diode. So V out as a function of V in, as V in goes from minus infinity to plus infinity. Well, if V in is negative, the diode is off, the output is 0, so nothing here. And then when V in reaches a large enough value, positive value, meaning VD on, the diode turns on. So around here the diode turns on, and From now on, we have a simple battery connecting the input and output if we use the constant voltage model, which means the output simply follows the input. So the output follows the input with a slope of 1. That's what we saw for the simple rectifier. Okay, now if we consider the time domain behavior of the circuit, meaning we apply a little, for example, sinusoid to the input, what does the output look like? So let me try to show you by a new color. So imagine that the input coming in here is a sinusoid, but a very small sinusoid, maybe 50 millivolts peak or something in that range. Remembering that VD on is about 700, 800 millivolts. Okay, so if we apply a little sinusoid like this as a function of time to the input, so here we have a little sinusoid like this, then what do we get at the output? Well, we follow these points and see that this point maps to 0, this point maps to 0, this point maps to 0. All of these points at the input map to 0 at the output. So if the input sinusoid has a small amplitude, the output is 0 at all time. Right? So that's the output. So that's not very good. There is a reason I wanted to rectify this waveform. I wanted to extract some information from it. But this says that regardless of how much amplitude I have here, as long as the amplitude is less than VD on, the output is 0, we have no information. We don't know whether this amplitude is 50 millivolts or 100 millivolts or 150 millivolts. We just have no information. So this rectifier has this blind zone, if you will. In this blind zone, we just don't see the input. We have no knowledge about it. So we would like to come up with a different type of rectifier, which we call a precision rectifier, that doesn't have this problem, meaning that if the input is small, if the swing is, let's say, 5 millivolts, 10 millivolts, and is positive, we let it go to the output. And if it's negative, we want to block it, just like a simple half-wave rectifier. So we are looking for a circuit whose transfer characteristic crosses 0 here. It doesn't have this dead zone or blind zone for the input range. All right, so let's see how we can do that. Okay, we'll take an op amp like before. We connect our input to the non-inverting input. We connect a resistor from the inverting input to ground. This is sort of similar to the non-inverting amplifier. But instead of a resistor connected between the input and the output, remember we had a resistive divider, I replaced that with a diode. So let me draw the diode like this. It might be easier to see it that way. Maybe I'll do it like this. We connect the diode like this. And the output of interest now is not here. The output of interest is here. So we'll call this V out with respect to ground. All right? So I claim that this circuit is a precision rectifier, meaning that when the input becomes a little positive, so even if the input is 5 millivolts, the output, this point, goes to 5 millivolts. As the input becomes more and more positive, the output follows it. And if the input becomes negative, the output is 0. So it's a sort of an ideal rectifier. Okay, so let's see how the circuit works. All right, well, what we can say is the following. We need to remember the fundamental properties of the op amp. The op amp says that if the output is always given by V in 1 minus V in 2 times A0. The difference between them times A0. If A0 is very large, we have, and V out is moderate, then V in 1 minus V in 2 is small. So we can say V in 1 and V in 2 are very close to each other. The difference between them is small. We're not bothered with that. All right, so here's how it goes. If this op amp has a high gain, so let's assume that A0 is high. then, and the circuit is working properly, then the difference between these two should be small. All right? Okay, so that's what we need to remember. This input sort of follows this input, because these two have to have a small difference. Whatever this guy does, this one wants to do the same thing. All right, so let's see how that happens. Let's suppose that V in is around 0. So I'm plotting V out as a function of V in. And I'm thinking the following. If V in is 0, well, the output is probably 0, so that's fine. But what if the input is, let's say, just a few millivolts, 2 millivolts, 5 millivolts, right? What if the input is here? Then what should the output be? All right, well, different possibilities, right? We can make a guess, proceed, and see if our guess is correct. So if V in is, let's say, plus 5 millivolts, one guess would be V out is 0, right? Meaning that this resistor carries no current, and V out is equal to 0. We know that this terminal doesn't carry a current anyway. Okay, so let's start from there and see if there's any contradiction. If V out is 0, and this gain is high, and this voltage is 0, and this voltage is plus 5 millivolts, then what should we have here? 5 millivolts minus 0, 5 millivolts, times, let's say 1,000. That's how much? 5 volts, right? So we have 5 millivolts minus 0 times 1,000, that's 5,000 millivolts, 5 volts here. All right, so it seems that under this situation, when this is 5 millivolts, this is 0, we should have 5 volts here. But is that possible? No, because if this is 5 volts, then what can we say about this diode? This diode sees 0 on the cathode side and 5 volts plus 5 volts on the anode side. That's not possible because this diode will turn on. If the diode turns on, it wants to maintain a difference of about 700, 800 millivolts. We cannot possibly have 5 volts here and 0 volts here. All right, so this point cannot be 0 if this is 5 millivolts. So what's the best guess we can make? Well, the best guess we can make is as follows. Let's suppose that we are right around here. In fact, let's even make it smaller. So let's assume that we are at 0.1 millivolt. All right, so this is 0.1 millivolt. What I will guess is that this point is also about 0.1 millivolt. Right? After all, we know that these two have to be close to each other. So that's what the op amp tries to do. And here's how it happens. If this terminal is 0.1 millivolt, and I'm guessing that this terminal wants to become 0.1 millivolt, because the difference between them should be small, and let's say this resistor is large, so that the current to this resistor is very small. So here's what we have to have. How could this terminal be 0.1 millivolt? Where does this voltage come from? Well, the way it comes from is from this output. If this is 0.1 millivolt and this is 0.1 millivolt, this diode will turn on with a very small current. Remember we said that when a diode is about to turn on or about to turn off, it has a voltage of VD on it, but its current is very small. So this diode is turned on, and it has a voltage of VD on here. So the output of the op amp is sitting at a voltage equal to VD on plus 0.1 millivolt. So that from here to here, we have a level shift of VD on. Then here we have 0.1 millivolt, which is close to this input, as required by proper op amp operation. And then that's what we have. The op amp is happy, everything is happy. Now, if we keep increasing V in, if we go to plus 5 millivolts, what happens? Well, at plus 5 millivolts, if this is plus 5 millivolts, this should be also approximately plus 5 millivolts. So now what happens is that this has gone up to a value equal to VD on plus 5 millivolts. So here we have VD on plus 5 millivolts. we lose VD on, and we get 5 millivolts. So as this voltage keeps rising, this voltage also rises, except that this voltage is always VD on above this voltage or this voltage. So V out follows V in with a good approximation. So V out follows V in because this op amp guarantees that the diode has turned on, and the op amp wants to pull this node with it. So this is similar to a unity gain buffer, except that from here to here we don't have a short circuit, we have a level shift of 800 millivolts. In other words, these two are not the same. They differ by 800 millivolts, but that 800 millivolts is relatively constant. So this goes up, this goes up, this goes up. The difference is about 800 millivolts, and the output tracks the input. The output follows the input. So as long as V in is positive, this is what happens, because it wants to make this point positive, and the op amp output goes up to turn on this diode, and we have a level shift. Now what happens if V in is negative? So if we are over here, so let's say V in is minus 5 millivolts. Well, can this point become minus 5 millivolts? Well, for this point to become minus 5 millivolts, we need to draw a current this way, right? It has to start from ground, flow through the resistor this way, and then it cannot go that way, it has to go this way. But that's not possible because this diode cannot conduct current in the opposite direction. So the diode has to be off. If the input is at minus 5 millivolts, the diode is off. If the diode is off, there's no current here. If there's no current here, V out is 0. So V out has to be 0. All right, so here we see that D1 is off, and V out is 0 because there's no current available to flow through this resistor. Whereas in this regime, what we really have is this. We have the op amp, we have a battery representing the diode, and then we have something like this. V in and V out. That's in this regime. So here, as V in goes up and down, this point wants to track this point because of the fundamental property of the op amp. These two inputs always have to be close to each other. So V out is close to V in. And the only thing that happens from here to here is a level shift of 800 millivolts. Whereas in this regime, we don't have a diode, so all we have is no current here, so this voltage is 0. All right? Okay. So that is what we call a precision rectifier, and it is used in applications where we have a small signal and we are interested in finding its amplitude. If I give you a signal, a sinusoid, and I say build some sort of circuitry that determines the amplitude, how would you do it? Well, the way we do this is that if we have this waveform by itself, with linear operations, it's difficult to determine this amplitude, so we have to have some nonlinear operation. So what we do is we first rectify it. Okay, and then we observe that if we find the average of this waveform, meaning this area divided by the period, obviously this area is in proportion to this amplitude, right? So first we rectify, then we find the average, meaning we low-pass filter it, and that gives us an indication of how large the signal is. This is very useful in cases where, for example, we are receiving a signal through our Bluetooth receiver, and we don't know if the signal is large or small. If you're close to a base station of a Bluetooth or something, or close to another transmitter, then we should have a moderate gain in our receiver. If we are very far and the signal that we're receiving is small, we should have a large gain in our receiver. And the way we determine what type of gain we should have is first by measuring the signal strength that is coming from the antenna. And signal strength means how large this swing is, or how large this swing is, or how much average we have here. So if we were to do this using a conventional rectifier, it would be hard because that requires that we have large swings. We have to go above 800 millivolts. Whereas with the precision rectifier, we have a much better situation, and we can rectify even smaller waveforms. Very well. So that's one acute example of op amps and how they can give us nonlinear operation using, of course, a nonlinear device such as a diode. All right, let me check here. And now let's go to another interesting circuit, which we call the logarithmic amplifier. A logarithmic amplifier. Now, what is logarithmic about it anyway? Well, what this means is that if we plot the input-output characteristic of this amplifier, so if we plot V out as a function of V in, for a conventional amplifier, it would be ideally like this. It's a straight line. That's what you would like to have for a simple amplifier, right? We like to have a straight line. That's what we call a linear amplifier. But for a logarithmic amplifier, when we plot it, we get something like this. So it's a nonlinear amplifier, and it has a higher gain here. As you can see, the slope is larger, and lower gain here. The slope is smaller. The utility of this becomes obvious if you are dealing with signals that come in, and sometimes the signals are very small and sometimes the signals are very large. In some applications, what we would like to do is amplify smaller signals by a larger amount and amplify larger signals by a smaller amount. And that's what it does. If you have a small signal coming in here, we have a larger gain. If we have a large signal coming in here, we have a smaller gain. All right? So let's see what kind of circuit can give us a logarithmic relationship between V out and V in. Okay, so here's how we will do it. We take an op amp, negative here, positive here. It's sort of like an inverting amplifier, but with some changes. So we have a resistor here. The positive side goes to ground. We are hoping to create a virtual ground here. And our input goes to the left terminal of R1. Then what we do is something peculiar. We go and buy a bipolar transistor. So here's a bipolar NPN transistor. We connect this emitter to the output. We connect this base to 0, to ground. And then we connect this collector to this voltage here. Strange, but that's what it does. Okay, so Q1. So I claim that V out is a logarithmic function of V in. So it has this type of behavior. All right, so let's see how that works. Okay, well, again, let's assume that the op amp is good. The op amp is working properly, so it satisfies this type of equation. Again, let's assume that the gain is very high. You can see that this assumption of high gain helps us so much in simplifying a circuit, even as complex as this, and quickly write the equations for it. Okay, so if that's the case, if A0 is high and V out is a moderate amount, then V in 1 minus V in 2 must be very small. So again, V in 1 minus V in 2 is very small, which means if V in 1 is close to 0, V in 2 is also close to 0, so we have a virtual ground. So that's a virtual ground. Okay, then we can calculate the current flowing through R1. We say V in minus this voltage over R1, but this voltage close to 0. So we say the current through R1, this current, so current through R1 is approximately equal to V in over R1. As we have seen a number of times in the previous circuits, the inverting amplifier, the integrator, etc. Okay, this current comes in from the input through R1 to the virtual ground node. It cannot go to the op amp. It has to go through this terminal and become the collector current of Q1. So this is equal to IC1. It has to happen that way, right? Okay, now we know that the collector current of Q1 can also be expressed in terms of its base emitter voltage. So we also know that IC1 is equal to IS, the reverse saturation current of this device, times exponential of VBE over VT. That we know. We can also make an observation here. There is a relationship between VBE and Vout. VBE is from here to here, from ground to this emitter. Vout is from this emitter to ground. So VBE and Vout are just negative of each other. So we have Vout or VBE equals to minus Vout. Okay, so now we combine these results and see what we get. We have Vin over R1 is equal to IS X of minus Vout over VT. And now we can find Vout in terms of Vin. So we see that Vout is equal to I divide by IS, take log of both sides, multiply by VT, multiply by minus 1. So we have Vin over R1 IS, then we have log, then we have minus VT. And this is the equation giving the output in terms of the input. And that is the input-output characteristic of the system, and it's a logarithmic behavior. Okay, that's interesting. So as I said, this has some application where we want to amplify smaller signals by a larger amount than larger signals. All right. Okay, let me see if there's any other point about this circuit. Now, here we have a log quantity. A log quantity would want to see that its argument is always positive, not even 0, right? Okay, so what happens if this Vin is negative? Well, this equation doesn't apply anymore, but what happens in the circuit? So if Vin is negative, so if Vin is negative, what happens? All right, so let's say that we still have a virtual ground here. Then a current begins to flow through R1 in this direction, because this side is lower than this side. All right, that current has to come this way through the transistor. But an NPN bipolar transistor is not capable of giving a current in this direction. So this transistor turns off. If this transistor turns off, this op amp has no control over this input anymore. This input is not a virtual ground anymore. So everything goes crazy. So if Vin less than 0, output of op amp is not defined. And by that we really mean what happens that now the output of the op amp goes all the way positive or all the way negative to some voltage, usually the supply voltage. So we say the op amp is saturated. So not defined meaning saturated. And of course it's not very useful. So the op amp is dead in a sense when that happens. So the input must be guaranteed to be greater than 0 at all time. If it goes below 0, then this feedback loop breaks, the output of the op amp goes to a very negative or very positive voltage, gets stuck there, and the circuit is useless. All right. So we have time for a quiz. Let's repeat this with a small change. So here's an op amp. We have our input resistor to virtual ground. And we have a bipolar transistor, but this time a PNP transistor. So here's a PNP transistor, and the base is still grounded, and we would like to write the output in terms of the input like before. I will give you 90 seconds. Okay, so what did you get for the answer? Well, we just repeat the same analysis as before. What we observe is that, again, this is hopefully a virtual ground. So virtual ground. And what we expect is that the PNP transistor can only deliver a current in this direction. So the current through R1 is allowed to flow only in this direction, which means Vin is allowed to be only negative, right? So let's write this current. This current is how much? This current is 0 minus Vin over R1. So this is minus Vin over R1, right? Previously it was Vin over R1 going this way, so it's minus Vin over R1 going that way, regardless of what Vin is. All right, now this current has to come from this bipolar transistor. So we can say that minus Vin1 over minus Vin over R1 is equal to the collector current of Q1. And how much is that current? That current is given by Is of the device times exponential of minus or plus VEB over VT. All right? So you have to make sure with PNP device you don't get confused over polarities. This has to be VEB because emitter is higher than the base, and I have chosen positive here because I'm looking at the collector going in this direction. All right? That current consists of holes. It's a positive current, so it has a positive sign here. Very well. So now we can go ahead and calculate V out nibs of V in, given that V out is equal to VEB. VEB is from here to here, and V out is also from here to ground. So in this case, it's just VEB. So that allows us to write, we divide by Is, multiply by Vt. So we have V out is equal to minus V in over R1 times Is, log of that times Vt. And this is what we get for this type of logarithmic amplifier. So in the previous version, the input had to be positive at all time. In this version, the input has to be negative at all time. That's the only difference between the two. Otherwise, they are very similar. So that's another interesting example of how we can use an op amp and some nonlinear device to create all sorts of interesting functions. In today's series on frontiers in electronics, we will look at some applications of op amps in what we call filters. There are numerous types of filter topologies that we can build for different applications, and many of these filters incorporate op amps in them. So before we go there, I wanted to refresh your memory about the circuit that we looked at a long time ago. We talked about this op amp called the 741 op amp, which is something like this or like this when you buy it. And it's pretty small. You can see that it's compared to a 1 penny coin, it's pretty small, or it comes in other types of packages. And in this op amp, we have a circuitry like this. Now, we are still not quite capable of analyzing all the details of the circuit. Yes, we have two inputs here. One input, non-inverting input, and inverting input. We have one output here, a positive supply, negative supply. Those are the basic things. We can barely work our way through the signal path to the output, but there are other types of topologies that we haven't seen yet. So let's start from maybe the inverting input and see if we can identify the stages according to what we have learned in this course. From the signal goes to the base of Q2 and evidently comes out of the emitter. So that's an emitter follower. Then it goes to the emitter of Q4 and comes out of the collector. So that's a common base stage. It has some sort of load, maybe a current source with degeneration, right? Then it comes out here and goes to another circuit. It goes to the base of Q15 and comes out of its emitter. You might call that an emitter follower. Then it goes to the base of Q17 and comes out of its collector. So that's a common emitter stage with degeneration. And then it comes here, goes to the base of Q10 and comes out of the emitter. So that's an emitter follower. So with our knowledge, we can sort of identify what's going on. But then there are other types of circuits here that don't seem very familiar. For example, this topology here, or this feedback here, this topology here, all of these. These are not familiar, and these are things that we will study in the next course, Electronic Circuits 2. But I just wanted to show you that inside that op amp, we have some structure like this. In fact, when I started learning about circuits some years ago, and I saw that one discrete transistor was like this, you could buy it, I was amazed that you could take 20 of these, you see Q20, right? 20 of these transistors, actually 22 of these transistors, and put them in a little package like this, which is smaller than a coin. So I was fascinated by that. I didn't know anything about integrated circuits and the abilities that we had back then or we have today. But it was quite interesting to me. Okay, so let's go and see how an op amp can be used in filter design. Well, where do we need filters anyway? So let me show you where we might use filters. Remember we talked about the task of measuring brain waves. And we said that every time a neuron fires, we have a small electric pulse on our brain. So the electric pulses might look like this. They have lots of this noise on them. You see this high frequency jumping up and down? That's noise, and I want to get rid of it. So we have to pass it through a filter to clean it up and make it look like this, right? So that's one application of filters, and you could build a filter using op amps. What you see on the bottom, which is not something that we have really studied in this course, is a filter. This filter has one input here, one output here. You can identify certain building blocks. You can see that this is sort of an inverting amplifier. This is one integrator, this is another integrator, but there's some other stuff is going on. There's a resistor here, there's a resistor here, all sorts of things. But that's one example of how we can build a filter to clean up the noise on a signal like that. and give us a clean signal. All right, but there are other interesting applications. Remember we talked about Bluetooth, and we said that when we have a receiver for Bluetooth, we are receiving a signal that's, let's say, around 2.4 gigahertz, and we need to process it. We have to give it to a low noise amplifier and then go to further processing. Well, but that's not exactly the only thing we have to worry about. So here's the situation. We have an antenna here. The antenna is picking up the received signal, and it gives it to the receiver. It gives it to the low noise amplifier and then the rest of the stuff. Unfortunately, when I'm receiving a Bluetooth signal like this at a certain frequency, 2.4 gigahertz, there could be other Bluetooth users around me, and they might be transmitting as well. So I'm trying to receive a signal. Let's say my laptop is trying to receive a signal from that printer, but at the same time there's another printer, another laptop close by that are also transmitting signals. So it's possible that my antenna is picking up my signal, the signal I want to get, but also another signal that I don't want to. And this is called an interferer. So how do I take this and not this? Well, at some point I have to filter this out, right? So that's another example of filtering. And for example, in this paper, they show that they have a cascade of 2 stages of filtering. These are called third order Butterworth filter here. And the filter is realized using an op amp. You see an integrator here with some feedback from resistors, some additional capacitors, etc. All right, so that's another example where we use an op amp to build a filter to allow to remove something we don't want. Usually a filter is to remove something we don't want or to let something in that we want. And these are some examples of that. All right, we are now ready to look at imperfections or non-idealities of op amps. So let me give you a quick list first. So we say op amp imperfections or non-idealities. The problem is that if we are not aware of these imperfections and we go and buy a 741 op amp and plug it in, the circuit may just not work. Remember, I gave you a cautionary note last time about the integrator. I said if you build this integrator as I have shown you in the lab, it won't work. And it is these imperfections that cause these problems. So we do need to understand the imperfections and then see what measures we should take to correct for them or avoid them. Okay, so the imperfections include finite gain. We have talked about this before. We said that if the gain of the op amp is not infinite, we had to do the calculations again for the amplifiers, etc. So that's fine. But there are other ones that we have not talked about. One is what we call DC offsets. The other is input bias currents. And the last one is finite speed. An ideal op amp would have infinite gain, no offset, no bias current, and infinite speed, but the real op amp doesn't. So we have to understand how these imperfections influence the performance or even the functionality of the circuit that we're trying to build. So we'll start with the DC offsets and see what they mean and how they affect things. All right, so let's change the color of our pen. And let's talk about DC offsets. All right, well, DC offsets are random voltages or random voltage that appear at the input of the op amp. And this is what we mean. If we go and plot the input output characteristic of an op amp, V in 1 minus V in 2, in the ideal case, this is what we have. Remember, we said the output is equal to V in 1 minus V in 2 times A0. But when we perform this measurement for an actual op amp, like a 741 that we just bought, we don't see that. We see something different. What we see looks like this. It's shifted this way, to the right or to the left. Or you can think of it as shifted down or shifted up, same thing. So in particular, when V in 1 is equal to V in 2, right here, the output is not 0. It's supposed to be 0, but it's not. Alternatively, we can say for the output to be 0, we have to change V in 1 minus V in 2 to a new value, to this value. Right? V in 1 equals V in 2 does not give us 0 V out. So to force V out to be 0, we have to add something between V in 1 and V in 2 to bring it to over here. And this is what we call the offset voltage, VOS. So that's what we call offset voltage. Now that's strange, right? Why does this happen? We didn't see this before when we studied op amps as a black box. Well, this has to do with the manufacturing process. So far, we have assumed that this op amp has perfectly symmetric circuitry, starting from here and starting from here, right? So, except that this is positive, this is negative, otherwise the circuitry should be perfectly symmetric. But that's not the case. Anytime you manufacture two nominally identical devices, there's bound to be some difference between them. So for example, even if you look at these two pens, which are nominally identical, well, if you measure their heights, they're not exactly the same. You measure the diameters, they're not exactly the same, and so on. So because of the tolerances that we have in manufacturing, there's always some mismatch, some asymmetry between two nominally identical devices. Now, if you remember, for the 741, we saw briefly that at this input, we have a structure like this. We had an emitter follower on the left, another one on the right, and then we had something like this, common base stages, etc. So again, we're not going through all the details, but what's important is that we are thinking that these two paths are symmetric. But when the circuit is built, manufactured, well, there are slight differences between these devices, so these two paths are not exactly the same. And because of that asymmetry, when this input is equal to this input, the output is not 0, the output is something else. All right? Okay, so that's the origin of these DC offsets that arise in the characteristic of an op amp. All right. Okay, so how do we model this? If we want to incorporate offset voltages in our calculations and our design, we have to have some sort of model. And the model is actually very simple. What we do is the following. We take an op amp symbol, and we just add a voltage source here, and we call it VOS. And presumably we know how much VOS is from the data sheet. The data sheet says that the offset voltage is, for example, 2 millivolts, 1 millivolt or something. So we put that here. And that represents the effect of the offset in the op amp. All right, so let me make a few observations here so that you're not totally confused. So, observations. Number one, this offset voltage is random, right? So when you build these two pens today, let's say this one is a little taller than this one, but when you build them tomorrow, this might be a little taller than this one. So this offset voltage, its value is random, even its sign is random. So when we say the offset voltage of this op amp 741 is, let's say, 2 millivolts, what does that mean? Well, it means that if we take many, many samples of 741 and measure their offsets, what we will see is that most of them seem to have an offset of less than approximately plus or minus 2 millivolts. All right, so it's a Gaussian distribution. Some of them have no offset, some of them have 0.1 millivolt offset, some of them have 3 millivolts of offset, but most of them seem to have an offset less than approximately plus minus 2 millivolts. So that's what we really mean by this. So there's a Gaussian distribution here for the offset voltage. And so the average is 0, the mean is 0, and then we have some distribution. So we say, yeah, so when we did the measurements, most of them were over here, and it was like plus 2 millivolts to minus 2 millivolts. Okay, so that's what we mean. All right, so VOS is random. And by random, we mean not only is its value somewhat random, its sign is also random. Okay? Now, because the sign is also random, it doesn't matter whether you put this plus here or here, or whether you place this voltage source in series with a non-inverting input or in series with the inverting input. It doesn't make any difference. Because VOS could be positive, could be negative anyway. So VOS can be placed in series with either input, right? It doesn't make any difference. So in fact, when we are analyzing circuits, including the offset voltage, we pick a terminal that's more convenient for analysis. So we might place it in series with this guy or in series with this guy, depending on what the circuit is doing. All right, so it's important to remember these about the offset voltage. Okay. All right, now it's good to look at the effect of this offset voltage on some of the familiar circuits that we have studied in the past. So let me go and show you some of these things. So effect of offset on amplifiers. All right, so we had a non-inverting amplifier, an inverting amplifier, a buffer, all these things. So we can go ahead and assume that the op amp has an offset voltage and then see what happens. All right, so let's start with the inverting amplifier. Here's our inverting amplifier, R1, R2, sorry, non-inverting amplifier, plus minus, V out. And I would like to choose one input of the op amp for the offset voltage that's more convenient. And it seems to me that it should be here. So I'll place the offset voltage here, VOS. And then, of course, I have V in as my main input. All right, so we go ahead and build the circuit. And we would like to see what the output contains. Well, because we have two voltage sources in series, we can just add them up. Or if you don't like, you can use superposition. So the total voltage that I measure from here to ground is VOS plus V in. So V out is the total voltage, V in plus VOS times 1 plus R1, R2 over R1, as we saw before. Okay. So this says that in a non-inverting amplifier, if we have an offset voltage in the op amp, that offset comes out amplified, just the way the input signal is amplified. If the input signal is amplified by a factor of 4, the offset is also amplified by a factor of 4. Sometimes that's a problem. If you are trying to measure a quantity that also has some significant DC in it, we're trying to measure the DC value, for example, but we add our own offset to this DC value, then we corrupt the signal, we corrupt our measurement. For example, let's suppose you have a voltmeter. A voltmeter is used to measure DC voltages, let's say the voltage of a battery. But inside the voltmeter, you have an amplifier like this, and it adds its own offset. So the reading that we get from that voltmeter will be incorrect, because in addition to the amplified input, it also has the amplified offset. So that's the manifestation of the offset voltage in a non-inverting amplifier. Okay. Now let's go ahead and look at an inverting amplifier and see what happens here. R1, R2, minus here, plus here, and that's the topology that we have, V out. And then this is V in. That's our that's our inverting amplifier. And we have to insert the offset voltage in series with one of these terminals. And it seems to be easier to do it here on this side. So we'll add the offset here, VOS, and see what we get. Okay, so again, we're looking to the output, trying to see what it contains. It contains an amplified copy of the input, and then it may contain something related to offset as well. How do I do that? Maybe superposition. So we set this to 0, and we say V out is equal to approximately minus R2 over R1 times V in. And then we set this to 0, and then we say V out is equal to what? Does this circuit look familiar? Yes, this is a non-inverting amplifier as far as VOS is concerned. VOS goes to the positive input of the op amp, and the output of the op amp goes through a voltage divider to the inverting input. So this circuit is the same as this circuit that we have here. Okay, sorry, I don't have it here. I have it here. This circuit is the same as this circuit, you see? If you compare the two, as far as VOS is concerned, VOS goes to the positive input of the op amp, and then the output of the op amp goes through a resistor, gets divided, and goes to another resistor to ground. So when V in is 0, that's what we get. So as far as VOS is concerned, we have a non-inverting amplifier. As far as V in is concerned, we have an inverting amplifier. Okay, so then that means that V out is equal to, VOS is set to 0, we have minus R2 over R1 times V in. And now we set V in to 0, we say VOS sees a non-inverting amplifier to the output. So that would be VOS times 1 plus R2 over R1. And that is the total that we have. Now, interestingly, in this case, the offset of the op amp is amplified even by a greater factor than the signal is amplified. You see that the signal sees a gain of R2 over R1, whereas the offset sees a gain of 1 plus R2 over R1. So the offset sees significant gain when it comes out, and it corrupts the signal. It corrupts the DC that we were trying to detect in this measurement. Okay, so that is the effect of offset on this type of amplifier. All right, our time is up. Next time we will continue to look at imperfections of op amps and how they influence some of the circuits that we have studied. I will see you next time.